he will talk about a new topic in relativistic quantum mechanics that arose from solid-state physics, and he's going to introduce us to the theory of graphene. Please.
Okay, thank you very much. Thank you for the invitation to come here. So first off, I should say I'm a theoretical physicist, so I will not even make any pretense of mathematical exactness. On the other hand, I think I've taken care of keeping everything so simple and elementary and clear that whenever you think that on the formal level some mathematical precision is lacking, not only can you complain, but probably you should be able to supply it yourself. Okay, so I've been given the task of giving an elementary introduction to the physics of graphene. So what is graphene? Graphene is simply a sheet, a two-dimensional sheet of carbon atoms arranged in a hexagonal lattice. And so that, that this structure could be interesting was realized even quite some years ago, namely half a century ago, roughly. But it was very hard to actually produce larger pieces of this structure, and so it was very important that back in about 2005, Geim and Novoselov from Manchester University came up with a method of actually a very simple method of producing these graphene sheets. And so since then there has been an explosion in experimental interest in this field, with many different structures being fabricated and many different physical effects being investigated on these graphene sheets. And from the point of view of applications, for example, they are very interesting because they have very superior mechanical properties. They are very strong. They also have very superior electronic properties, so electrons move for very long distances without being scattered, so that makes the electrical resistance quite low. However, from the point of view of a theoretical physicist, and I also guess from the point of view of a mathematician, what's so interesting about those is that the physics of electron waves is governed by the 2D Dirac equation for massless particles in these graphene sheets. Now, let me give you an outline of what I'm going to discuss. I will first start with the most basic information about electron waves in graphene. That is, how does the band structure look like, and where does the Dirac equation come in? And then, when we are done with the homogeneous case of an infinitely extended graphene lattice, we want to study, for example, what happens if electric fields are applied so that potentials are generated and electrons might be repelled by these potentials, and that may influence their motion. And then we will learn about another issue that is very important to the motion of electron waves, namely the boundaries of graphene. It turns out that the boundaries are also very interesting because they can support what is called edge states. And then finally, as the last topic I will discuss, we want to have a look at what happens in a magnetic field. There will be a quantum Hall effect, as you expect for any electron system in 2 dimensions, but it will have some peculiar properties that are associated with precisely this Dirac structure. And then finally, very finally, I will mention in a brief overview a collection of other topics that are of current interest in graphene. Now, you can read all of this and much more in a very comprehensive review that has been written back in 2009, and in particular Novoselov and Geim were involved, and a few theoretical physicists as well, where you can find these issues, even though there are some typos in this review, I should warn you. Okay, so before I start, let me tell you that you are invited to ask questions throughout the talk, and I'm aware that there is a kind of language barrier. So you can ask questions not only about the concepts, but please also ask questions about words, simply. Okay. Now, if we look at this lattice, it's not really important that we're dealing with carbon atoms. Actually, it turns out that if you forget about all the inner electrons that make up a carbon atom, what we really should care about are electrons residing in exactly one orbital sticking out of the plane, out of each carbon atom, and then there can be tunnel coupling between the different orbitals so that electrons can really move between the different carbon atoms. So it will be these electrons that are able to move by hopping from side to side that we will care about. And what is the most important point about this structure? Well, the most important point here is the threefold symmetry which you have at each lattice site. So to start off, we will not even look at the full lattice, but we will look at a very simple quantum mechanical problem, namely taking one of those lattice sites and its three neighbors. Okay, so one lattice site and its three neighbors. I colored them differently, but of course in the lattice they are all equivalent. Now, when I want to describe this quantum mechanically, regarding the motion of a single particle on these four lattice sites, I will just deal with a very simple problem, namely I have a four-dimensional Hilbert space. And my wave vector has one complex amplitude for each of these four lattice sites. So if I denote the central site by r, that's the position of the central site, then psi of r is supposed to be the complex wave amplitude for the central site. And likewise, there will be a wave amplitude up here, psi of r plus delta 1, psi of r plus delta 2, psi of r plus delta 3. So I want to start by writing down the Schrödinger equation, more precisely the time-independent Schrödinger equation. So I want to figure out the energy eigenvalues of this problem. And as you know, the time-independent Schrödinger equation would have the form E, that is the energy eigenvalue, times wave function equals the action of the Hamiltonian onto the wave function. So I have to figure out what is the action of the Hamiltonian. And the only physical process that should be contained in this Hamiltonian is simply the fact that a particle is allowed to jump from here to there. And of course, it's also allowed to jump back again, because the Hamiltonian has to be Hermitian. Both processes must be allowed. So for example, let's pick the central lattice site. If I write down the time-independent Schrödinger equation, I will get four equations. For each of the lattice sites, there will be one equation corresponding to the action of the Hamiltonian on the wave function evaluated at that particular lattice site. So let's pick first the central lattice site. So E, the energy, times psi of r equals everything that I collect by acting with my Hamiltonian on the wave function. So the central lattice site has, so to speak, a particle coming in from all of the other three sites. So the tunnel coupling connects to all of the three other sites, and I will get a contribution from the amplitude psi of r plus delta 1, psi of r plus delta 2, psi of r plus delta 3. We will assume, as is the case, that all the tunnel amplitudes are the same. All directions are equally good. And there will be a value associated with the strength of tunneling, which has the dimension of an energy, which here conventionally we call T for tunneling. And the minus sign is also, if you like, a convention, but it makes sense physically because what you want to have, or what you know in advance, is that the wave function that should minimize the energy should be one that has, say, positive values all over space, the same value all over space. The wave vector equals 0 wave function. So minus t, there is some physics behind this choice, but it's not very important for us. You would get the same results if you were to choose a different sign here. Okay, so these are the contributions from all the different lattice sites if we pick the central site. And then, of course, there are three more equations. I've written down only one of them. For example, the equation that we get if we look at the lattice site up there. So energy times psi of r plus delta 1 equals, again, all the contributions we collect by the action of the Hamiltonian, which denotes the hopping between sides. But there's only one side where I can originate from in order to hop to the outer side up there, and that is the central side. So that is minus t, the tunneling matrix element, times psi of r. Okay. So if you prefer, since this is just a four-dimensional Hilbert space, I could write down the Hamiltonian, and the Hamiltonian would have the structure, a real symmetric Hamiltonian, where I picked the order of my basis such that the first basis vector would correspond to the central side. So it's a very simple Hamiltonian, and now you could try to work out the energy eigenvalues and eigenvectors yourself. Yes, please?
Will depend on the exact distance center to center, so this whole t could be actually not really the same t per vibration. You're
oh, yes.
A total symmetric.
Yes, okay. That's a very, very pertinent remark. So assuming that I have the same tunneling matrix elements is because I know about the symmetry and all the lengths are the same. Of course, later on, if you were to consider a distorted lattice, either statically distorted or by vibrations, then it would exactly mean that these tunnel coupling matrix elements become different. And then, for example, one of the things you can worry about is, well, here it would be fairly easy to insert this effect. But later on, we will go to the Dirac equation, and then you will have to think about how the distortion enters the Dirac equation. Okay, so maybe you have even worked out the eigenvalues of this problem already. But what I want to point out is, in particular, we get energy equals 0 as an eigenvalue, and that can be seen easily. How do we see easily that energy equals 0 is an eigenvalue of this problem? Well, I claim that we can make this happen by destructive interference. So I claim that we can pick the amplitudes at these three red lattice sides such that if I add them all up to get the right-hand side in this equation, they add up to 0. And there are several ways to arrange this, but a nice and symmetrical way to do this would be to pick complex phases, that is, complex numbers of equal magnitude at the three sides in such a way that they add up to 0. And so here I just picked the third roots of -1, I guess. Here and in the following, I will always have this pictorial representation for complex numbers. So I will display an arrow whose direction is just given by the phase. Yeah? And so if you want to add these three complex numbers of unit magnitude, you could as well just add these three vectors, and you will see that they add up to 0. So that's destructive interference. So then I get 0 on the right-hand side, so the energy must be 0. On the other hand, I will also pick 0 on the central lattice side, because then I know that in all these other equations, I will also get 0 on the right-hand side, so that everything is consistent, and energy equals 0 is really a correct eigenvalue. Okay? So that's very important, this destructive interference. Now, there is not only one eigenvector for energy 0. There will be two. How can I see that? Well, you see, there's a certain kind of handedness to the situation. So, for example, if I imagine I traverse all those red sides in a clockwise direction like this, I can ask, what does my arrow do? What does my complex phase do? And as you see, the complex phase then will also be traversed in a clockwise direction in this example. But I can as well choose different directions, such when I traverse the sides in a clockwise direction, the complex phase will just do the opposite. And that's really an orthogonal eigenvector. And so the energy 0 here is doubly degenerate. And this will happen again, and this will become important. So there are these two clockwise and counterclockwise solutions for energy 0. Okay, so is that clear? Okay, good. Now, the funny thing about this construction is you can also extend it to the lattice. look here. So in this lattice, I denote every other side by A and the rest of the sides by B. These are two sublattices. And the structure of the hexagonal lattice is such that A sides only connect to B sides and B sides only connect to A sides. Now, if you pick any particular B side, which would correspond to what we called the central lattice side a moment ago, and you add up these vectors, again, you will get 0. You can check that this is the case for any B side. And again, there will be two possibilities, because I can have this kind of clockwise arrangement or a counterclockwise arrangement. Okay. Now let's attack the full problem. So what we want to do is do what every physicist would do when faced with a problem like this, write down what we call a tight binding model, which is just a model where we only pick localized orbitals at the different sites and claim that they are coupled by tunneling. And so we write down the time-independent Schrödinger equation. Now, for convenience, I will always denote whether the particular site I'm talking about is on the B sublattice or on the A sublattice. Okay? Even though, of course, by giving the position, I could tell immediately, so this subscript is slightly superfluous. Okay, so whenever I'm at a B point, I just pick up contributions from all the surrounding A points, and correspondingly, if I am at an A point, I will pick up contributions from all the surrounding B points. And if you think about it more carefully, then the locations of these B points, calculated with respect to this A point, I obtain when I subtract these difference vectors. So R minus delta 1, R minus delta 2, and so on. So that's only a slight detail. Now, you know the structure is supposed to be infinitely extended, so every physicist would automatically do a plane wave ansatz, which means that psi of R is basically e to the I chi R with an arbitrary wave vector k, but then multiplied with some as yet unknown amplitude psi A, and the same for psi B. And so if you insert this ansatz here, you will find that, well, this ansatz works. For every k, there will be two energy eigenvalues. These will be obtained by diagonalizing a complex Hermitian 2x2 matrix, whose entries then depend on k. I have not shown the matrix here, but what you get out are two bands, as we say, two energy eigenvalues for each particular choice of the wave vector k. And they are given here, plus minus a square root of some function of kx and ky. And as you can see here, this was done a very long time ago when no one was yet able to produce the material in the laboratory. Okay, so before showing this function, we already know that we expect points where the energy touches down to 0. Yeah. This is not immediately obvious by looking at this. If, for example, f were always very small, then you would have plus minus square root of something, so you would have two bands that are separated by a gap, and this is actually what you expect in the generic case, but here it will be special, and we already proved that there will be 0 energy eigenvalues from our consideration of destructive interference. So here is this function, the lines of constant energy plotted as a function of kx and ky. There are points where the energy is 0. We will say more about them in a minute. Apart from that, this pattern is periodic. So this kind of hexagonal pattern would repeat periodically in the space kx and ky. And that means not only the energy eigenvalues repeat periodically, but also the corresponding wave functions repeat periodically. And all I should focus on is one unit cell of this lattice, and that would be given by what we call the Briand zone. That is just the hexagon shown here. Now, there are these 6 spots where the energy happens to be 0 in the picture shown here. But they are not really 6 different spots, because as you can see by investigating the Briand zone, if I pick the surroundings of this point, which I denoted capital K, you see that only 1/3 of its surroundings are part of my Brillouin zone. And so it has an equivalent point here and another equivalent point down here. All of those really correspond to the same physics, to the same wave number. So these 3 points are supposed to be equivalent, and there are 3 other points denoted by k prime, which are also among themselves equivalent. So the wave functions you get are the same. Okay, so we really have only 2 equivalent points in my Brillouin zone, where the energy touches down to 0. And now you can plot the same kind of function in a 3-dimensional fashion, which is done here, energy versus kx and ky. Again, you see that at these special points, the energy bands touch. The reason they don't touch at 0 here is that this particular plot was done by assuming not only tunneling between nearest neighbors, but even between next nearest neighbor sites. And as you can see, this does not spoil the important structure which is shown here, namely that the 2 energy bands happen to touch at these points. And the way they touch is also very interesting. If we zoom in, we see that they touch in the form of 2 cones whose tips coincide. So these are called Dirac cones because they correspond to what you would expect for the spectrum of a Dirac operator with 0 mass. And indeed, the energy near these cones is plus or minus the wave number as measured from the tip times a velocity. And this will really be the velocity at which electron waves move. And the velocity you could express by the tunneling matrix element and by the distance between the sites. And I should mention here that I've set h bar equals 1. So the tunneling matrix element here would be like a frequency times a length has the dimensions of a velocity. Okay. Yes, please.
Why is it the velocity at which the electrons move? Why is it?
Oh, you mean how to prove this?
Or just to understand?
Yeah. Well, first of all, if I have any kind of waves and I plot frequency versus wave number, and I have a relation like this, then, so to speak, from experience, I know that those waves move at this velocity. For example, if I were to construct wave packets, I would see that the center of mass of the wave packet would precisely move at this velocity. It's exactly the same with simple sound waves, for example, or photons. For photons, this would be the speed of light. I should also mention that the velocity given here, of course, has nothing to do with the speed of light. If I were to consider real relativistic particles with 0 mass, then the velocity would necessarily have to be the speed of light. But here it's actually 300 times smaller than the speed of light. It's given by these material constants. Okay. Now, I already mentioned that the situation here is not the generic one. The generic one would surely be that I get 2 bands, because the original hexagonal lattice should be viewed as a simple periodic lattice which has 2 atoms inside the unit cell, and this automatically gives you 2 bands in such a tight binding description. But the 2 bands usually would not touch. And you can understand that very easily, because at each value of the wave vector, as I said, we have to diagonalize a complex Hermitian 2x2 matrix. How many parameters are in a complex Hermitian 2x2 matrix? Well, I would say 4, but if you disregard the total energy offset by which I can shift the energy eigenvalues up and down, there are really 3 independent real parameters. And all of the 3 would have to be 0 in order to have a degeneracy. But I only vary 2 parameters, kx and ky, so that generically would not give me degeneracy between the 2 bands, because 3 parameters are supposed to be 0 at the same point simultaneously. So we will come back to that. So this is not something that happens generically. Now, in order to understand that, let's have a look again at the wave functions, also in order to bring out the difference between these k and k prime points. So again, imagine you move in a clockwise fashion and ask, how does the complex phase behave? Yeah. So here I plotted a situation where the complex phase also moves around in a clockwise fashion. And if you really look at the wave functions, for example, at the k point, you will see that if I move around in a clockwise fashion around B, the phase evolves clockwise. If I pick a point on the A sublattice and I do the same, then I would see that the phase moves around counterclockwise. And at the k prime point, exactly the opposite happens. So this is somehow a handedness attached to these two different points. And so there's always a clockwise circulation counteracted by a counterclockwise circulation, and the roles of A and B are just inverted when I go from k to k prime. Okay? So this is shown here again, a wave function near the k point on the lattice. And these belong to energy 0. So this is because of the destructive interference. For example, if I add up all these blue arrows to give rise to the total contribution arriving at the central spot, that will give 0. And the same happens if I add up all the red arriving at the blue spot and all the blues arriving at the red spot. And now, since we are dealing with destructive interference, this also means that I can arbitrarily change the relative phase between the blue and the red. That doesn't change the argument about destructive interference, because destructive interference happens just by adding up all the red contributions, for example. And when they add up to 0, I don't really care what's the relative phase between blue and red. Yeah? So because I can arbitrarily change the phase between the blue and the red sublattice, and I still remain at the k point, that just means there's not only one energy 0 function there, there are two eigenfunctions for energy 0 there. It's doubly degenerate, just like in the original problem, just like with the problem for 4 lattice sites. And if I have two bands and some k point where I can prove that the energy is doubly degenerate, that just means that the bands have to touch. And as you can see, this is very much connected with the underlying symmetry. For example, it's also not spoiled if I introduce not just the nearest neighbor coupling, but also the next nearest neighbor coupling. Then you can convince yourself that if I add up the contributions from all of these next nearest neighbors, well, let's see. If I want to collect contributions to here, then this, and this, and this, and this, and this, and that one will be the next nearest neighbors. And if you work it out for the wave function shown here, you will find that you will get a contribution which is no longer 0, but which just happens to point in the direction opposite to this arrow. And that is fine, because that then also reproduces the wave function at this point up to a prefactor, and that defines the energy. Yeah. So these considerations give you a lot of information about what is special about this hexagonal lattice. Okay. Now, so much for the tight binding model. Now we want to make the step to the Dirac equation. And that is, we want to focus on the vicinity of these Dirac cones. That is, we want to focus on wave functions that already have a wave vector close to these special wave vectors where we have doubly degenerate eigenvalues. So what you should imagine is that if I have a wave vector very close by, or I add up the contributions of many wave vectors close by to the special point, what I arrive with is a wave function which basically oscillates, which has a very fast oscillation corresponding to the wave vector at this special point, and a slow envelope variation. Yeah? So for example, if I were to write down psi of r on the B sublattice, and I want to remain at energies near 0, which means at wave vectors very close to these two special points, then I can split into two contributions, one coming from around the k point, one coming from around the k prime point, each of them being multiplied by a function that is slowly varying to only give small, tiny corrections to this wave vector k, for example. So if I decompose this in a Fourier decomposition, it will always have very small wave numbers whose length is much, much smaller than the wave number k. Okay? And I can do the same for psi a. Here I have had to sneak in some phase factors to make the resulting equations look nice in the way I set up the geometry. But this is the important part, that I have a slow variation. And then I want to just insert this as an ansatz into the time-independent Schrödinger equation of my tight binding model, the one which we already solved. And so after inserting, what I exploit is, of course, the fact that these wave functions here are slowly varying. So if I evaluate them at some point r plus delta, I can Taylor expand. So I can say, oh, this is just to first order in delta, delta times the gradient of this slowly varying wave function. So this is all I do when I insert into the time-independent Schrödinger equation. Okay? And so then the resulting equations I get are of this structure first, that I add up contributions from all three surrounding sites, but now for each of those contributions, I implement the approximation given here, that is, I Taylor expand and have the gradient. Okay? Okay, so all that remains is just to then carry out these sums over all the surrounding, over all the neighboring lattice sites. Or I should say that starting from this point, I have assumed that little r can really vary continuously in space, whereas previously capital R, of course, was always only centered on the discrete lattice sites. But that is fine since I have such a slowly varying function. Okay, so what you obtain if you carry out the sums is just the Dirac equation. So you always have two contributions, one on the A sublattice, another one on the B sublattice. There are no contributions in this approximation that connect the k and the k prime point, so I can say focus for a moment only on the contributions from the k point. So the wave function has now become, so to speak, a spinor wave function with two components, one for the A, one for the B sublattice. And the derivatives that appear happen to mix B and A. So these derivatives will act on the B component and give a contribution to the A component up there. Okay, so in a simplified notation, and this is the notation we use, I would say that I have the gradient vector containing d over dx and d over dy, and I multiply it with a vector containing the first two Pauli matrices, that is sigma x 0, 1, 1, 0, being multiplied with d over dx, and sigma y with minus y and minus I and I being responsible for these derivatives with respect to y. Okay, so that is the Dirac equation in 2 dimensions for particles without mass. And the funny thing, of course, about the Dirac equation is that if you write it down in 1 or 2 dimensions, you get away with simple Pauli matrices. If you go to 3 dimensions, as you all know, you need these 4 by 4 gamma matrices. But here you get away with simple Pauli matrices. That happens to be the correct equation at the k point. If you go to the k prime point, it turns out you just have to replace minus I d over dy by plus I d over dy. Okay? But for all of the following, we will mostly focus on only one of those 2 points, because the reasoning will be that whenever I only have, say, potentials that vary very slowly on the scale of the lattice spacing, then there will be never any scattering processes that take me from k to k prime, because the corresponding change in wave vector would have to be very large. And this will be excluded if I have a slowly varying potential. So that's why I can focus, say, just on the K point. Okay. Any questions so far? Yes, please.
Just to check, this is still on a lattice, so R takes values on this.
Oh, no. This is supposed to be with little r already being continuous.
What's the meaning of the amplitude at points where there's no carbon atom?
There is no particular meaning to that. In the end, of course, if you were to go back to the physical problem, you would just evaluate this function at the particular lattice points. But in order to be able to talk about these derivatives, I want to imagine that little r is just continuous. At least to a physicist, that seems reasonable enough. Otherwise, I would probably have to express d over dx as a difference quotient between different lattice points. Yes?
You mentioned that something different will happen in 3D.
Yes.
That you will need a spinner maybe or something. I thought you still just describe a massless particle by a wild spinner with two components in 3D. Nothing terrible happens in 3D.
Oh, okay. So my remark was a general remark about the Dirac equation, by which I mean the Dirac equation of an electron, where I'm really forced to take the 4x4.
Particles.
Okay, thank you for the remark, yeah. But here, even if you were to take mass, it works with Pauli matrices. Maybe that's the remark I wanted to make. Thank you. Okay. So now just to check whether everything is all right, we want to quickly diagonalize this Hamiltonian. We go into the equations with a plane wave ansatz that is psi, which is a spinor, times e to the I qr. Q now is supposed to denote the difference in wave number to the K point. So this is a very small wave number in magnitude. Then we have every derivative gets replaced by the corresponding component of Q, and I immediately see that a 2x2 matrix of this kind will have energies E equals plus or minus velocity times magnitude of Q. It's equal, so we get the Dirac cones, and it's equally interesting to have a look at the corresponding eigenvectors. Yeah? So the eigenvectors have equal magnitude for the A and B sublattice components in each case. The only way that the direction Q enters is that it enters as a phase factor here. So that's a phase factor with the phase given by the angle in the qx, qy plane. And the difference between the upper and the lower cone then enters in the difference sign down here. Okay? So that's very nice. We recover the same result we already found in the tight binding model. Now, one further remark here. If we look at the Hamiltonian is basically something like sigma times the gradient, that is sigma times the momentum operator. So if I define sigma times the momentum operator divided by the magnitude of the momentum operator, that happens to be a conserved quantity for this Hamiltonian. So it commutes with the Hamiltonian. And it happens to be positive, +1, for every state in the upper Dirac cone and -1 for every state in the lower Dirac cone. So in itself, of course, that doesn't seem like any great insight that helps us at this point. But it does help once you introduce a very smooth, slowly varying potential. Because if the potential is slow enough, then, for example, you don't scatter from one K point to another K point. We already remarked on that. But also, you don't usually scatter easily from one direction to the opposite direction. This is simply because the scattering would change the value of P, but it would not change the value of sigma if the potential is slow enough that it doesn't really do anything different for the A sublattice than for the B sublattice. So it can't act on the A and B sublattice indices. And then the helicity would suddenly change, and then you would find that you have orthogonality between the initial wave function and the final wave function. so these scattering processes are suppressed. So everything that does happen is, if you have a slowly varying potential, is that very slowly the velocity or the momentum of the electron changes because it's deflected by the potential, by the forces generated by the potential. Okay? And as it is deflected, the helicity still remains conserved in this approximation. So that means the kind of spin defined here always points along the direction of motion or opposite to it. And there's one remark here. This is not the real electron spin, of course. We haven't even been talking about the real electron spin. You can imagine that the real spin of these electrons just has a fixed direction, which, to a good approximation, doesn't change as the electron travels along. This is a kind of pseudo-spin. It's connected to these A and B sublattice degrees of freedom. Okay? But once this has been said that this is a pseudo-spin, it really behaves like the real spin of a real electron when there is spin-orbit coupling, when the orbital motion influences the spin of the electron. And so this is the extreme case where the influence of the orbital motion on the spin is so strong that the spin is always forced to point into the same direction as the orbital motion. And now this has important consequences. So what are the consequences? Well, you might know that spin 1/2 is kind of funny. So if I take a spin 1/2, think of the real spin of an electron or of a neutron, and I just turn it around by 360 degrees so that the spin again points in the same direction, then the wave function acquires an extra phase of pi. So this can be seen most easily in a situation where, say, you have an external magnetic field that forces the electron spin to point parallel to the magnetic field to minimize the energy. And then you slowly change the direction of the magnetic field. Then the spin is made to follow the direction of the magnetic field. But there will be this extra phase factor of pi that is accumulated beyond the dynamical phase that you would always have. So psi is supposed to be the spinor describing my spin 1/2 particle, and after a 360-degree rotation, I will find that this is the original psi, but it has a phase accumulated because at each point in time, I have a certain energy that would be connected to the magnitude of the magnetic field. That is the dynamical phase. That is, so to speak, the simple part that you would always expect. Plus, there will be an extra part, this extra phase of pi, and that's the specialty of spin 1/2. So if this is true for real spins, it's also true for this pseudo-spin. And in particular, it will be true if you take a full circle in your motion. So if the motion looks like this, you started out here. The spin always has to follow, and in the end, the spin again points into the same direction. But there will be this extra global phase factor in front of the wave function. Now, because it's a global phase factor just in front of the wave function, it wouldn't matter, for example, for observables like the expected spin direction. The expected spin direction is just the same as in the beginning. But it does matter whenever we have interference. And that's also the way it has been observed, say, in neutron interferometers. And so it turns out that this phase factor becomes important later on when we will describe the particle in a magnetic field, because in a magnetic field, this is exactly what happens. The electrons are forced to turn in a circle. So this is one issue where the helicity comes into play. There are other examples. For example, if these electron waves are scattered from a disordered potential, then usually in quantum mechanics you would have constructive interference of backscattered waves, which enhances the electrical resistance above and beyond the value that you would expect from a classical consideration, which is called weak localization. And now here you would find that because of destructive interference, actually you reduce the electrical resistance. So these are two examples where this extra phase will matter. Okay. So much for solving the single particle Dirac equation. Before the break, let me begin to say what happens if you have a potential. Excuse me. But before I can tell you what happens if I have a potential, we should just acknowledge the fact that, of course, there is more than one electron in the system. So what happens is that, for example, at 0 temperature, I take the given number of electrons and I fill up all states until the number of electrons is exhausted, starting from the lowest energy state. And the highest energy I can come up with is called the Fermi energy. And now it turns out that if graphene is neutral, if there are no extra electrons, then the Fermi energy lies exactly at the Dirac cone, at the spot where the two cones touch. So that's the usual situation. All electron states below this point are filled. All electron states above this point are empty. And whenever we have a situation like that, we know, for example, that all single particle observables, like the density, can be simply obtained by summing over the contributions of all filled orbitals. So I would say the density is the sum over all filled states, psi squared, giving the contribution of each filled state. Okay? Yes, please.
Excuse me, can you explain this a little, why the Fermi energy is exactly at this cone point?
Okay. So there is exactly, this is simple, there is exactly one free electron per carbon atom.
Yes.
And so I have these, so automatically I have these two bands, and I will always expect to have only one of them filled in this case. Because I have, okay, now I should bring in the real electron spin. So there will be one electron per carbon atom. Half of them will be spin up, half of them will be spin down. So if I only focus, say, on the spin up electrons, which I'm allowed to do because there are no processes considered that mix the different spin directions, then there will be one spin up electron per two lattice sides. And that is automatically half filling in the sense that I have these two bands, but I only should fill, say, the lower band. Yeah. So actually, here's a place where the real electron spin finally enters, but only in determining the number of electrons that come into play. Okay. Otherwise, of course, if both of the bands would be full, then I would have simply an insulator, because the next bands would lie higher up, and I would need a finite energy to excite electrons from here to up there. Okay, so simple counting, not forgetting the real electron spin, gives you the result that the Fermi energy just lies at the tip of the cone. Now what happens if we add a potential? And again, let's assume the potential is sufficiently slowly varying that it doesn't make a difference between the A and the B sublattices. So it varies on length scales much longer than the distance between neighboring lattice sides. And then I can very simply insert the potential energy in my Dirac equation. So I would have V times the momentum, V times sigma times the momentum, plus the potential energy that depends on the position. So everything that happens will be that I shift up or down the band structure. And so that's the picture you should have. My potential shifts up these two cones. But if I do so only in a certain region of my system, the Fermi energy is still the same all over the system, because the Fermi energy is really determined by the bulk of the system, where it's still at zero. So the Fermi energy in equilibrium will always be the same everywhere in space. But at points where my potential, for example, pushes up in energy all my states, this automatically means that a few of the states in the lower cone would remain unfilled. So this is the typical situation if I apply a potential somewhere. Okay. Now, what happens when I apply a potential? Usually, we expect that a potential can generate a barrier that is hard for the waves to penetrate. And that is very important for applications because often I want to confine my electrons to a small region, which then would be called a quantum dot, and do something special to those electrons. So it's important to ask about barriers in any kind of material. Now, first let's have a look at simple non-relativistic electrons with a finite mass. That is the Schrödinger problem with a potential barrier. And we imagine that an electron at energy E comes in, so there will be an incoming wave. And then most of the wave will be backscattered, and only a little bit will penetrate the barrier due to quantum mechanical tunneling. So that is the standard situation. But the way I want to plot it here is a little bit different than usual. I don't want to keep the barrier fixed and change the energy and ask about the transmission. Rather, I want to keep the energy fixed, and then I change the height of the barrier. So if the barrier is very low, if V is much smaller than E, then the wave will practically be perfectly transmitted. There will be slight reflection that depends on how sharp your barrier profile is actually. Yeah. Now, as I increase the barrier height, at some point there will be the point where V matches the energy, and afterwards the barrier is actually higher than the energy, and this is the region where classically every particle would be reflected, but quantum mechanically I can still have tunneling. However, the tunneling will be suppressed exponentially as I further increase the barrier. And so that is the situation: first perfect transmission, and then tunneling and quick suppression of the transmission. So that is the textbook problem. Now, what happens for relativistic electrons, but still real relativistic electrons with a finite mass in 3D, described by the Dirac equation? Now, there will be, like for our case with the two Dirac cones, there will be the positron band of energies smaller than 0, and an electron band of energies larger than 0, and there will be a gap between them, quite unlike our situation given by the mass. So now, again, if I send an electron towards a barrier, there can be the possibility of tunneling, and if the barrier is not very high, like here, at first I will simply observe what I already know from the non-relativistic Schrödinger equation. Now, at some point though, the barrier will be so high that the positron band, that the upper boundary of the positron band in energy goes below 0, which means now that something dramatic happened, namely that the transmission suddenly shoots up again to unity. This is physically, so to speak, unexpected intuitively, but it can then be explained, namely saying that if an electron comes in, there's only a small region corresponding to this gap where it would be forbidden to propagate, whereas inside the barrier there is a large region where there are actually states of the 3D Dirac equation where the wave can propagate, and so it only has to overcome these tiny little barriers, which even become smaller as the original barrier height becomes larger, and so that is how 3D Dirac electrons can really be transmitted through the barriers by practically unit transmission if the barrier height is large enough. So that is known as Klein tunneling. Okay, and now we want to see, do we have something similar for our case? Of course, there will be no threshold like this because simply our mass is 0. Still, we can ask what happens. Okay, so maybe this is the last slide before the break. Now, in order to describe Klein tunneling, you would proceed in very much the same way as for your standard textbook problem, even in the non-relativistic case. That is, you would say, I have waves incident from the left, and to make things more interesting, I really want to treat the full two-dimensional situation. so the wave can be incident at an angle. There will be a reflected wave as well, so the total wave function in this region will consist of the incoming and the reflected wave. Inside the barrier, there will also be a right-going and left-going wave. They have the same wave number, the same component of the wave vector in the y direction that is parallel to the barrier, simply because there the system is still translationally invariant. They can have and must have different values of the wave number in the x direction, simply in order to conserve energy. And then in the third region, which is supposed to be back at the old potential, we just have a right-going transmitted wave. And the purpose of the calculation is to calculate the amplitude of the transmitted wave, or rather the factor between the amplitude of the transmitted wave and the amplitude of the incoming wave. That is the transmission amplitude. Okay? And just one remark about the calculation. Usually for the Schrödinger equation, at the boundaries between the regions, you would match both the wave function and the gradient of the wave function. Here we are dealing with a Dirac equation. You only have to match the wave function. Only the wave function has to be continuous. That is all you can demand for this first order equation. And so now this is the plot that results by solving this problem. That is the transmission probability, the square of the transmission amplitude, as a function of the incident angle. You see a relatively complicated structure, but in particular you see that if the angle is 0, that is, if you have perfectly normal incidence along this purple line directly head-on onto the barrier, then you get perfect transmission. Then you get perfect transmission at every energy. And so maybe at this point, let me stop the first half of the tutorial, unless there are still questions.
Other questions, please.
So the equation you get is stationary, but it's what you would have gotten if you took the standard 2 plus 1 dimensional Lorentz invariant Dirac equation, separated variables. And so there's a Lorentz invariance in there with the speed of light replaced by this.
Yes. Yes.
How is that interpreted? So there's no preferred frame, but we've got this.
Oh, yeah. So this equation on its own would look Lorentz invariant, but physically this doesn't really help you very much. For example, as soon as you have the interaction between the electrons, that would be the standard Coulomb interaction mediated by the standard electromagnetic field, which has the standard speed of light. So these are, so to speak, not compatible. Also, if you start interacting with the phonons, they are not proceeding at this particular velocity, but at their own acoustic sound velocity. So as soon as you start considering interesting interactions, the total theory is no longer Lorentz invariant with respect to this velocity.
But there's no consequence of that. Nothing physical that you can get out of that.
Well, you would say that things like conservation of the helicity are a consequence of that, because you find something similar for the real Dirac equation. So as long as you remain with the electron waves around these Dirac points, there are all these analogies that come from the Dirac equation itself. But it's actually an interesting thought that if you were to have, say, also sound waves with exactly the same velocity, and if the interaction between these electrons and the sound waves were dominating any other thing like Coulomb interaction, then you would have a relativistic theory with the real speed of light replaced by this velocity.
Where do these other point of perfect transmission come from? So not only the...
Oh, okay. I can't give any particular reasoning for that. I forgot to mention that these are calculated for different barrier heights, and it seems that these other points do depend very much on the relation between the incident energy and the barrier height, whereas the perfect transmission at a normal incidence, that is reversed.
Is the helicity related to any kind of notedness or anything like that?
Any kind of
notedness of entanglement or something like that.
That's probably a question that should be addressed to mathematicians. I don't know. I don't have any deeper understanding of this helicity, except that it comes from the special structure of this lattice with the special structure of these wave functions.
There's one more question here, yes.
And if you get some higher barrier, you lose more transmission, more points where there is a perfect transmission, or I mean, here we have either 3 points or 5.
Oh, okay. That's a good question. So, you are asking, say, if I were to reduce the barrier height. Now, I don't remember here what was the fixed finite energy this was calculated for. We could go back to the review and actually just have a look at the formula, and then I could answer whether we get more and more of these perfect transmission points.
Well, I guess the coffee is calling. We reconvene at 4. Thanks.